Hello, my name is Ovidiu Ștefan Gogu, and I'll be holding a 20-minute presentation on identifying and describing hand tools associated with fitting and assembling. This is a presentation that I'll be holding as an interview. At the end of this presentation, the students will know how to identify and correctly use hand tools required to assemble parallel rails according to assembly drawings, examine and study working drawings, measure and mark drilling points, machine drill holes, tap threads, and ream dowel holes, and align rails within 1/100th of a millimeter tolerance. For a quick overview of this presentation, I'll start by going over an example of using hand tools on a specific task. Then I'll describe the tools selected for the task in detail and for a better understanding of their safe and correct use, and go through the steps of completing the task. For a better understanding of the use of hand tools associated with fitting and assembly, I'm going to explain their use for a specific task as shown in Figure 1. In this task, I'm going to explain how we can assemble two rails on a support plate by manually marking out drill points on the plate and machine threaded holes to assemble the rails, aligning the rails to be parallel, and perform dowel finishing to fix the rail in parallel position. So this is the support plate, this is the pair of rails, and we are going to measure and mark drill points and perform the threaded holes and the dowel holes. We have to keep in mind that the center line of the rail has to be within 1/100th of a millimeter parallelism geometric tolerance, and the distance between has to be in 0.4 millimeter dimensional tolerance and equally spaced on the plate. For measuring tools, I'm going to select a vernier caliper. These are some of the most used tools capable of measuring external dimensions, internal dimensions, and depths. Besides the two pair of measuring jaws and the depth gauge, its main features include a main scale and a vernier scale. The resolution of the vernier scale is determined by the difference in distance of the division on the main scale and the division on the vernier, as shown in Figure 3. Usually, a vernier scale of length 39 mm is divided into 20 equal divisions, so one division on the vernier represents 1/20th of 39 mm, which is 1/95 mm. While two divisions on the main scale represent 2 mm. So the resolution of the vernier is 0.05 mm. That's 5/100th of a millimeter. When we measure, we read from the 0 on the vernier to the left on the main scale to get the full millimeters, and to the right on the vernier to get the decimal that aligns to the main scale. For example, 15/45 millimeters on Figure 3. Before use, a vernier caliper should be checked for calibration to make sure that it is working correctly. After use, it is important that you check the beam of your vernier caliper for any unwanted residue that may affect the sliding motion of the vernier scale. Apply a small drop of oil to the beam of the caliper and clean it off with a cloth. A vernier caliper should be stored somewhere dry and humid-free, like a protective case, to keep it safe from when not in use. As marking tools, I have selected scriber, dot punch, and center punch. A scriber is used for scratching lines onto the workpiece. They are most commonly used to mark out metal workpieces due to their advantages over this type of material because scribed lines are far thinner, so they are more accurate and shallow scratches that can be smeared or rubbed off. Engineered scribes have a sharp tip point that may be made of tool steel, hardened steel, or occasionally diamond, enabling them to scribe lines on hard surfaces such as metal. Before use, a scriber should be checked to have a sharp undamaged tip. To use the scriber, you have to hold it as you would a pen, as shown in Figure 4. At an angle of 45 to the workpiece, place the tip up against the edge of the ruler, keeping the tip of the scriber up against the edge. Move the scriber across the workpiece in the direction you have scriber head tilted, and apply enough pressure to keep the tip in contact with the surface. This will produce a neat thin line that will be dark in contrast to the brighter surface of the workpiece, or vice versa. There are two types of punch, namely dot punch and center punch. A punch has a point angle of 60 degrees, and it is used for marking of small precise dots on the reference line. The center punch has a point angle of 90 degrees, and it is used for marking a large indent on a workpiece for drilling. Both punches are made of hardened tool steel. Before use, the center punch and dot punch are checked to have sharp and damaged tip. Because the drill has the tendency to warp if it does not start in a recess, a dot punch is used to produce a narrow and deep indentation, as shown at point 2 here. After that, the center punch is used to enlarge that indentation into a dimple by placing the narrow end onto the target point and striking it with a hammer or a mallet, causing the blunt force of the blow to be transmitted down the rod body and focused more sharply onto a small area. We're going to perform the measuring and marking as shown in figure 6. The objective is to draw two parallel lines within 0.4 mm tolerance placed on the center of the support plate and mark drill points on them. So first we are going to select the datum on this side, and using a vernier caliper we are going to measure the width of the plate and establish the center. Measure the place of the first rail center line from the center and then the place of the second center line. We will use a tri-square to draw lines perpendicular to the datum, and we will use scriber to scratch thin lines on the support plate where the center lines are placed. It is a good practice not to go for the full line in the first try and have short lines done first that we can check and make sure they are within the geometrical and dimensional tolerance. Once we have the center lines on the support plates, we use the vernier caliper again to measure the distance of the holes from the datum. We use a dot punch to mark the place of the holes, and we use a center punch, this one, to open the holes into small indentations so the drill does not walk from the position. If we don't know the distance between the holes on the rails, an accurate way to measure is to use the vernier caliper to measure the inside of the farthest points and of the closest points to the holes and divide the sum by 2 to get the center of the holes. As cutting tools, I have selected twist drills, spot drills, and taps. Drilling is the process of cutting holes in metals by using a drilling machine. Drills are the tools used to cut away fine shapings of material as the drill advances in rotational motion through the material. Drills are made of high-speed steel, hardened carbon steel, tempered and coated. Other drills have inserts of cemented carbide to form cutting edges or are made from sintered carbide rods. The angle of the tip is designated for specific types of materials. As we can see, we have 60 degrees for plastics, 90 degrees for non-ferrous materials and wood, 180 degrees for general purpose, and 135 degrees for hard and tough materials. The twist drill is made up of 3 parts: the shank, the upper part that fits into the machine, the body is the area between the shank and the point with twists running along to carry away the chips of metal, and the point, which is the end of the drill bit that does the cutting. It is made up of lips that are sharpened cutting blades to form the tip angle, and heels, the larger supporting area behind the lips, ground back to give relief of about 12 degrees. Spot drills are designated to be extremely rigid so that they can precisely spot a hole for a twist drill. Maximum grip on the shank keeps them on target to make a pilot dimple in the workpiece that keeps the twist drill from walking so that the hole is accurately located. It can also be used to chamfer holes, and it's preferred to the center drill because the point of the spot drill is at 45 degrees to the center line, and it makes it easy to calculate the depth to radius ratio. So if we have a 5 diameter hole, we go to the depth of 2.5 to touch the diameter, and we go further to produce the chamfer. To use the drills correctly, it is very important that the drill points are central, the lip angles are equal, the cutting edges are unchipped, and the clearance angle is correct. To obtain this state and ensure correct angles, it is important that drills are ground in a grinding machine. To perform any drilling operation in a safely manner, tools must be clamped in the drill chuck tightly. The workpiece to be drilled must be firmly secured by vise or clamps. The drill guard or protection must be closed before switching on the machine. For any drilling operation, use the correct drilling speed and apply suitable drilling force. It is advisable to lift the drill occasionally and clear the hole of cutting swarf. Apply cutting fluid in the cutting except for drilling cast iron. Take care when the drill is nearly penetrated through the workpiece, the screw-in action can lift up the workpiece. And taps. They are used to cut internal screw threads and are made of high-speed steel or hardened high-carbon steel. The end of the shank is square to fit a wrench. Usually taps are provided in sets of 3, as shown in figure 11. The tapper tap is tapered of a length of 8 to 10 threads, and it is the first tap to be used in a hole and start a thread form. The second tap is tapered off to a length of 4 or 5 threads to facilitate picking up the threads cut by the tapper tap, and the plug tap is fully threaded throughout its length, and it is called the bottoming tap. This tap is used to cut the bottom of the blind hole. Precautions when operating a tap: in addition to drilling, the size of the hole it is important, and the correct drill size should be determined from the handbook, standard table in the workshop, or the recommendation on the shank of the tap. Lubricant oil should be used except when cutting cast iron and brass. Use both hands to hold the wrench to maintain even torque. About every half turn, reverse action slightly to break the swarf and clear the threads. When the tap reaches the bottom of the blind hole, care must be taken not to force the tap, as taps may break in the hole. Now we are going to machine the drills and the taps. As we can see, we have our plate with the lines and the drill points marked out, and the objective is to machine the holes on the marking from the support plate. First, we're going to place the correct drill on the column drilling machine, in this case a 4.2 diameter drill for M5 threads. We're going to place the marked plate with the center punch marking under the drill tip. We're going to gently pull on the lever to touch the center of the drill with the center of the punch marking. Now, manually, we are going to align the center of the drill with the center of the punch marking, and I have to add here, if we're using a 4.2 diameter drill, the center punch marking is enough, but if we were to use a bigger drill like a 10 diameter drill, then a center drill would be recommended first on the center punch marking. Since this is not the case, we are going to put the drill directly, and after we have manually aligned the center punch marking with the tip of the drill, we are going to fix the plate in place by gripping it to the table with a parallel jaw or clamps. And using the correct and safe indications for drilling, we're going to perform the drilling and tapping of the M5 threads and 7.5 mm diameter holes for 8 mm dowels. Now, again, we need a measurement instrument, a dial indicator in this case, and they are one of the primary measurement tools used in precision building. They are typically used to measure flatness, parallelism, concentricity, and other measurements that involve the distance between surfaces. The dial indicator uses a calibrated stem to transfer linear movement to the dial face that has graduated hash marks. The most commonly used type of dial indicator is between 1/1000th and 5/1000th of an inch, or 2/1000th and 1/100th of a millimeter, depending on the build, so that one revolution on the indicator needle usually equals 0.1 inch or millimeter travel. In figure 13, we can see a dial indicator that takes the measurement vertically, a comparator that takes the measurement the same way, and a test dial indicator that takes the measurement lateral. An accurate use of a dial indicator requires rigid mounting and absolute stability. If the indicator moves at all while the measurement is being taken, the measurement is compromised. Hence, dial indicators are almost always used with an adjustable magnetic base that can be clamped firmly to a nearby surface. The magnetic base can be adjusted to position the dial indicator so that the stem can read movement in the same direction as the part being measured, and so that it can read travel in both directions by adjusting the stem about midway in its range of travel against the part being measured. The most important part is to zero the indicator prior to every measurement. You do this by rotating the outer dial to position the zero mark directly on the needle regardless of where it's pointing. Once the indicator is zeroed, you can take the measurement by moving the part in question, and the indicator will show movement either positive or negative. So in this step, we are going to line the rails and tighten the screws. First, we assemble the rails on the support plate, and we tighten the screws on one rail, right on this case, and we leave them loose on the other, left one in this case. We put the cage on the rail and the adjustable magnetic base on the cage. We adjust the dial indicator so to have the stem touching on the loose rail on the straight surface that we want to line, and zero it in. We slightly tighten the screw on the side that we start the measurement with, this side. We slide the cage on the rail to the other side, and we notice the measurement on the dial. In this case, it's 0.15 millimeters counterclockwise. That means that the rail has moved to the right. After we know the misalignment, we tap the rail with a soft face object not to damage the surface, till we get the dial to measure less than 1/100th of a millimeter. Because the screw is slightly tightened where we started the measurement, it's a good chance that the rail will rotate on that point and align on the other side, and it's going to save us time in aligning the rail. We repeat this until we get the rails parallel within less than 1/100th of a millimeter. This is possible because the holes of the M5 threads allow for movement. In this case, 5.5 mm holes minus 5 mm screw allows for 0.25 mm movement on one side. If it's not possible to align the left rail to the right, then we tighten the screws on the closest alignment, we loosen the screws on the right rail, and repeat the alignment on that rail. In this way, we have 0.5 mm movement in which we can align the rails. The last tool we're going to use is a reamer, and they are used to control the diameter of a hole, improve internal surface finish, or the roundness of the hole. Reamer is made of hardened high-carbon steel or high-speed steel. They can be hand reamers and machine reamers. Hand reamers has two types of flutes, straight and spiral flutes. The spiral flute reamer has a left-hand spiral flute to prevent reamer screwing action in the hole. Machine reamer has a straight shank or a tapered shank, a Morse taper. The taper shank fits directly into the spindle of a machine, while the straight shank is held by the collet. To perform operation with a reamer in a safely manner, in addition to drilling, care the sharp cutting edge, especially in handling. The amount of material to be removed by a reamer should be as small as possible, between 0.1 and 0.5 millimeters. Reamer must only be turned in one direction, both in and out of the cutting. Otherwise, the tool may jam. Lubricant oil should be used except when cutting cast iron and brass. Ramming can enlarge the size of the hole but cannot correct the position error in drilling. And because of this, we can machine and assemble the dowels. We go through the same process of machining holes on a column drill, only this time with a reamer, and because the dowel holes are already machined on the rails, the reamer will fit in the holes and continue the 8 mm dowel hole through the 7.5 mm hole even if it's misaligned, as shown in figure 16. After the holes are machined, the dowels are placed by hand in the dowel holes, and this will help with the rail fixing on the plate and also help future rails to be assembled on the plate without the alignment process. Now, as an overview, we have measured and marked drill points on a support plate. Then we have machined threaded holes, assembled and aligned the rails, and finished the dowel holes. To assemble this according to the assembly tolerance draft. I hope you enjoyed my video, and remember to have fun at work.